let's say you've been given the position vector of a particle. Let's say this is your position vector and the particle is moving like this. So initially it starts at time equals 0. After 1 second it would have traveled this much of a distance, and then another second it would have traveled this much of a distance, and after 3 seconds it will end up here. So the particle is traveling like this. And we know the formula of the arc length is given by this. So if you want to know the distance traveled in the first three seconds, then you would integrate it from 0 to 3. So we've seen this formula before. This is our arc length, and we can rewrite this. We can rewrite this. We can rewrite this as this. We can rewrite this as this. Nothing special, just a different notation. So we've already seen that the arc length is given by this. So we could, if we wanted to, create a function. We can create some sort of machine where we insert a time. You insert a time, and then it will do something, and then it spits out the arc length, because we have a formula for the arc length. So let's say if you put in the number 2 in here, so after 2 seconds, we can actually work out the distance traveled. It would be this distance here after 2 seconds. So you insert a time 2, and then it will do whatever it has to do to spit out an arc length. So we can create a function where you insert a time, it will work out the distance traveled. So we normally use this s for distance traveled, the length along the path as s. Okay, so hang on. So we can create this sort of machine, this function where if you insert a time, it will give you the arc length, which is given by this. But the thing is, we can't leave it as it is like this. We can't leave it as it is. We need to change this t to a different variable, u, and change this t here to u. Change this to u, because at the moment it clashes with this. So rather than integrating with respect to t, we would integrate it with respect to u. So let me explain this step here. Let me explain this step. At the moment we can't do this because this t here clashes with this t here. So we change everything in here to u, and then use, because this, well, let me explain this part here. So remember, from when you first started out with the fundamental theorem of calculus, you were trying to understand why if you have a function like this and you're trying to work out the area underneath a function, you wanted to know why there's a connection between the area and the antiderivative of the function. So you would create this new function here where you let x here be a variable, so you can slide x back and forth. You can slide x back and forth. But the problem is that this x clashes with this x. So you would then change this thing here to f of t rather than f of x, and then change this to change dx to dt. And then back then you never really understood why you're able to change, why you need to change f of x to f of t and d of x to d of t. So let's consider this. Let's consider f of x equals x squared. So we want to create a function where we can slide x back and forth, and depending on where x is, it will work out this area. So we would define a function like this, where this is the most important thing here. This allows us to slide x back and forth. But if you don't change the f of x, look what happens. Normally, in order to get this to work, we normally change this to t squared dt. But let's leave it as f of x and see what happens. So when you integrate this, it will then give you this from a to x, from a to x. But then when you come to put this into here, what does it become? Does it become x to the power of 4 or over 3? Take away a cubed over 3, or well, what do you do here? Because you see, this is there's something fishy going on here, which doesn't make sense. Now, if you consider this, so you've got your function f of x equals x squared. You're trying to find a way of working out this area. So now rather than, well, if you change f of x to f of t, so now change this to t squared dt. Integrate this with respect to t, it will then give you this, and now when you put x into here, it becomes x to the power of 3 over 3 and so on. Nothing clashes here. It makes perfect sense, and you're still preserving this x squared thing, this t squared thing. You're still preserving it. Nothing really changed. You're just changing the name. So back to this thing here. Back to this thing here. Hang on. Back to this thing here. We're trying to create a function where you insert a time and then it spits out the arc length. Well, we've got a formula for the arc length, but then we want to be able to slide t back and forth. So we need to change this to a u, change this to a u. Everything will be preserved. It's just we are just changing the name. We're just changing the name. Everything will be preserved. So hang on. So now we can work out. So for a given time, you insert a time, we can work out the arc length. So let's say t equals 2.8. Well, we can put 2.8 into here, or we can put it into here, and then it will work out the distance traveled along the path. So it will give us this distance here along that path. So hang on. So we can create something like this. You insert a time, and then we would do this whole thing here, and then it will spit out an arc length for us. It will spit out an arc length. We insert a time, do whatever we have to do, it will spit out an arc length. It is possible by following this formula here. Currently, you don't really understand what's going on here. You need to see an example, which I will give you in the next video. But then if you, well, at the moment we've got a function, or we've got some sort of machine where we insert a time, it will be able to give us an arc length. So it is also possible for us to create a machine where we insert an arc length. So let's say the particle is traveling like this. So let's say this is t equals 2.8. If you put 2.8 into here, we can work out the arc length, which is this thing here. But now the clever part, it is possible for you to insert an arc length. So you can create a machine where you insert an arc length. So now we insert the arc length. We can work backwards. So we're inserting an arc length, which is, remember, our t equals 2.8 here. We can insert this arc length here. Insert the arc length. We can work backwards to find out the time it takes to travel that distance along the path, which in our case is 2.8. And once we know the time, we can put it back into here. We can put the time back into here to work out the position of the particle right at that moment in time. So the point here is that we can create a machine, a function, or whatever, where we insert an arc length. We can work backwards to find out the time, and then once we've got the time, we can stick it back into here. We can stick it back into here to find the location of the particle. So this thing here is written as this, s of t. So you insert a time, and then s is the distance along the path. So we can work out the distance along the path. Now to write this, we would write it like this: r dash s t. So this thing here is your arc length. So when you insert an arc length, it will do whatever it has to do, and it will give you the position vector, which is in a way the location. Okay. For you to really understand this, I need to give you an example, which I will do in the next video. Okay.